Let's go ahead and then move on. So the next presentation is going to be provided by Zachary Morse. And Zachary, I apologize if there are multiple co-authors. I've dropped your abstract, but I see you're going to be speaking about augmented reality visualization of geologic data collected with portable field instruments. The floor is yours.
Thank you, and I am. Let's see if I, hopefully you can see and hear me all right, and yes. I'll share my screen quickly. Share. So with any luck, you are seeing my presentation. And yes, just in case, so my name is Zach Morse. This is going to be a chat about some work I've been doing with integrating data from portable instruments, similar to what Sheree just talked about, into a new and interesting way to view that data in the field. My co-authors are listed here. I'm actually a postdoc with Howard University, working with the RISE-2 group at NASA Goddard. And this is sort of an interesting story to tell, because this is not, the work I'm talking about is not what I was brought on to do. Mostly I was meant to help out with field work, going to Kilburn Hole, like Sheree just talked about, but that all got put on hold due to the pandemic. So this is an interesting, I wouldn't say makeshift, but work that we did in the interim, sort of being a little creative with the time we had. And so it's also an interesting method to describe. It's complex to describe, but very easy to show if I was able to show this application in person. So I'll do my best. But that begins with a description of what we do as field geologists in the field, which I'm sure most of you already know. You have your field geologist, and you head to a real world outcrop, be that Kilburn Hole or any of the other field sites we've heard about today. And you usually have some data, and that can be compositional data, numbers, graphs. It can be field notes from folks who have been there before. It can be remote sensing data or geologic maps. And more likely, usually it's a combination of all of these things and more. And it's the responsibility of the field geologist to analyze these data and then interpret the surroundings around them and figure out how each of these pieces fits into the real world scene in front of them. And so looking ahead to future fieldwork with us and potentially analog missions with astronauts or real astronauts someday, we want to save as much time as we can in that mental interpretation stage. So what this project is doing is trying to compress all of that into one, essentially a tablet or a smartphone view of all of the data in real time, sort of like almost like a geographic information system for a rock outcrop. And one thing that this, oh, there it is, AR data visualization. So one thing that this has advantage over a traditional GIS is, with a traditional GIS, you're looking at a map view. If you're moving around a field site, in this case, Kilburn Hole, at different locations, you can put a point on the map and it all shows up very well. But if you're in a situation such as this, where you're doing a vertical transect of multiple layers, adding those points to a map gets to be confusing. It can be a cluster of points right on top of one another. But what this application we're developing does is it takes that same sort of GIS view where you can sort through different data types and interact with the data and applies it to a vertical surface in real time in front of you. So each of these field flags becomes a digital point, and each of those points is linked to the data that was collected there. And as a benefit, that link remains as long as the outcrop is in existence. So you could return to this field site in a week or a month or a year or two, and the data would still be linked there without having to leave a field flag or a field marker in place. So how does this all work? It's a bit tricky to explain, but if we go back to our example with the field geologist with an iPad, essentially the iPad acts as both a screen to view data and a camera to view the world. And so the application activates the camera, and the camera begins looking around. And we program in what we call a digital image target, which is essentially just a digital image of a real world outcrop or a collection of pixels that the camera can match to what it's seeing in the real world. And as soon as those pixels match, the application automatically overlays data that we've put into it that has been previously collected this outcrop and overlays that data on the screen in real time. And so what this looks like in reality, I have a quick video, hopefully this will play, is something like this, where you have, and this is just an example, a retaining wall in my backyard. Since we couldn't do field work during the pandemic, again, this is sort of makeshift, do as much as we can with what we could. So you'll see you can move around different perspectives, the data stays in place. If you get too close, it loses tracking on the image, so the data disappears. But then you step back and it sees enough pixels, it knows where to place the data, and you can see in this case, an image overlay of the wall itself. But we can work with individual data points or images to overlay the data. So back to the title of this program, overlaying data from handheld instruments. Around April, we were starting to be able to at least get back to center at Goddard, and I was responsible for working with a new instrument that we have to take on field excursions, TerraSpec Halo. It's a portable field spectrometer. It can record data in visible and near-infrared wavelengths, and it gives you real-time data analysis. Within seconds, you can see a spectrum on the screen of the rock that you are scanning. And so I thought this would be a good opportunity to go from a false outcrop in my backyard and false data to a real outcrop in the real world with real data and try and integrate that together. So the first step is getting the instrument. Next, I needed an outcrop. So I found this rock outcrop nearby my home. It's actually right on the Appalachian Trail near Harpers Ferry, West Virginia. It's actually a metamorphosed sandstone, part of the Harper group. So it's not the most geologically interesting rock, at least in terms of planetary science, but I guess, as they say, any port in a storm or any rock outcrop in the middle of a pandemic will do. So we proceeded to do what I think is probably the first field work that has been done at Goddard since everything shut down last March. Use the spectrometer to take points across the rock. And as you'll see in this close-up image, there are visible variations. You have tan sections, you have red sections. So a first order hypothesis here is are the spectra for these locations the same? Are they different? What can we learn really quickly and then integrate that data into augmented reality? So in PowerPoint, this is very easy. You can draw an arrow, you can put the spectrum right on the screen. And so for the presentation, you all can see this, but the trick is to do this in real time for field geologists in the field. So what we do is we take, again, the digital image target. Each point, I had to record not only the data, but the point where that data was collected from, link those to the spectra that are saved, that were exported from the instrument, and then integrate it into a video for you all to show everyone. So in, hopefully it will not get stuck. See if I can get it to replay. Oh, this is the big crux of the presentation. Well, I will advance it as best we can. So what you'll see here is there's actually a few sun flares at the beginning, so hopefully I can actually skip over that. I'm not sure why it is not automatically playing, but what this does is it overlays individual points which remain in place on the outcrop even as you change perspective.
6 minutes.
Perfect, right on time. Here we go, and it started to play. So you'll see these points remain in place. These each represent a spot where I took a spectrum from the outcrop, and you can get really close up. In the field, you would actually be holding an iPad with this data on it, but in order to show this, I've just recorded the screen directly from my laptop. And if you click on any of these points, the spectrum is now shows up. So it's linked to the exact point on the rock where it was taken, and anyone with a tablet with this app on it can view these spectrum. So it takes that data from being sort of bottlenecked either from the spectrometer itself or from a laptop, and makes it available for multiple members of a field party to view and analyze. And as you might have seen really quickly, it was sort of a quick video test here, but despite the visual differences in the rock, the spectra are all very similar. So similar composition. There's a control panel at the bottom, so you can turn on and off different points and look right at the rock itself. But yeah, this takes the data and applies it right in front of you for everyone to view and interpret. So next steps with this, obviously, we next want to integrate data from multiple instrument sources. This was just a first step, but you can imagine a full field deployment with multiple instruments going. You could have that all linked, and so different teams can view and understand different sources of data all right at the outcrop face. Hopefully, moving on to, right now we use just the static image target, but hopefully in the future we'll be able to take 3D scans of the outcrops and then link the data to a 3D model, which will help with some of the jittering or stuttering you may have seen. That was also partly due to trying to record this at the same time as using the app, so I apologize for that. But hopefully also in the future integrating this into a HoloLens for your sort of heads-up display or hands-free visualization of data in the field, maybe integrating it into an analog mission scenario. And finally, more field work, and more importantly, getting it into the hands of field geologists to get input, feedback, and improve the user experience so that this can actually become a tool that we use on a regular basis in the field. And so with that, I think I'm practically out of time, so I will end here with a very quick example that just says thank you, and if there are any questions, I'll take those. So thanks.
Okay, Zach, thank you. We have a minute and a half left in your time. I'm the only one who asked the question for you, so let me go ahead and consume that time. In a field exercise at Meteor Crater, we had a test subject that was so focused on the task of taking pictures of a boulder for kind of producing the type of product that you just described. He didn't make observations of the rock himself. And his observations of the rock itself would have changed the traverse if he had been paying attention to making his own observations. And so in that case, the data collection interfered with traverse productivity. And I'm wondering if you've encountered the same phenomenon, and if so, have you found a way to mitigate the problem?
So it's a good thing to know about. We actually, since all of this work has been done since the pandemic started, I haven't had a chance to deploy this at a real field excursion. And so I would say that the way that hopefully this will be mitigated is that this application works by integrating mostly data from a previous field excursion. So be that field photos, notes, spectra that were previously collected, and then can be compiled in a database so that on your second trip or the next day you go out, you have easy access to pre-recorded data. So in that case, you're not necessarily focused on collecting data for the app. You are just focused on collecting data as a field geologist that you might want for future research or for future notes. And then we take that and we kind of collect all of it and integrate it together to provide just a new way to visualize the data. So hopefully, my hope is that this will become a useful tool for reference rather than collection in real time. But any data that is collected that has a visible component could be integrated into this for future visualization.
Okay, thank you very much.